Alright, time for another DraftPhysics.com video presentation. So the Ian Gosling has made a rather, almost a reasonable video about some of the complications of doing these experiments to tweeze out the truth about this distinction. Now, if we had the simple experiment, like 9 times the fuel to go 3 times as fast, or collecting the energy from something going 10 miles an hour and then collect the energy from something going 30 miles an hour and see how much damage it does, how much impact it has, and measure the calories of heat it produces, let's say. And then we could have this definitive proof that yes, there's 9 times the heat created by something going 3 times faster. We don't have those experiments, and so we have to do the ones that are more possible and more simpler. All right, and the fact is these haven't been done either, and they really should have been done well by scientists, and we shouldn't have to do them, rig them together, and that is unfortunate. But anyway, so play the video.
Hello guys. At the risk of this being a convoluted video with too many subjects in it, just briefly, Gary, I tend to do your...
They're all valid subjects, okay, in the sense that every experiment has these little variables, and figuring out the difference between the big one is in all these experiments of mechanical objects is colliding things in gravity, moving things in gravity, and then trying to figure out, well, moving things out of gravity, where you're measuring motion that isn't supposed to be affected by gravity. And frankly, yeah, there's advantages and disadvantages to switching between the two, because they both have liabilities.
Rolling disc experiment.
So I don't know if rolling is the best idea, but yes, I mean spinning. So you could figure if you put a wheel, bicycle wheel, horizontally, and then tied a rope around a spindle and had it go down a pulley, and you pulled it with a weight. I mean, theoretically, because it's the same amount of velocity and mass that you're moving, the two would be the same. So maybe you could use a bigger... Yeah, I mean, the idea is you need to separate the distance. It needs to be a real difference in the distance between the two weights, because the smaller the distance, the smaller the effect. So, blah, blah, blah. But I think
with masses in different positions, 2 discs, and race them. See if there's a difference in the speed they do down the ramp.
So, I mean, the thing here, with the holes in it, maybe you could just shove lead in the hole. So put in 4 holes, and then 2 holes closer, and shove lead in there, or some other kind of bolts or something of the same, find 6 bolts that have the same mass, right? No. Yeah, I mean, all you want to do is you want to put 4 on the outside and just 2 on the inside. No, the other way around. Yeah, right. You want 2 on the outside and 4 on the inside. And see if those 2 would roll the same. So 1 wheel with 2 bolts on the outside and 1 wheel with 4 bolts on the inside. So that kind of thing. But a lot of ways to do it. Like I said, the bicycle wheel thing you had before was probably a good enough setup. Especially if you could turn that horizontally to do it both ways. Do it vertically and then do it horizontally. Now, I don't think gravity can make a difference. Even though it's a lighter mass on the outside, theoretically, you're not moving it 4 times the height, but you are moving it twice the velocity. But the point is, it's in the gravity the same amount of time. So the heavy mass and the light mass will be in the gravity the same amount of time, and obviously gravity is only going to affect the half mass half as much. So the half mass would have an advantage because it's the same amount of time in the gravity. It's really not about how much distance you move height-wise. It's really about how much gravity you're fighting over time. So it gets a little complicated. Right there it gets a little complicated. Is the time more important? And how much of the time are you spending going sideways, which isn't working against gravity, and how much time are you spending going up and down. So that's the part that gets a little tricky. I am just trying to think for myself if there's much theoretical difference in the amount of time two things are in the gravity. But anyway, in the end, you only lifted it twice as high. You didn't lift it 4 times as high. So you didn't do as much work on the lighter object. So you could theoretically say there'd be a slight advantage when you initiate the action. But once the action goes full circle, it compensates because you dropped the masses the same as you lifted the masses. So you got gravity pushed down the same amount as you had to do work against. It's just that you had to put the original work in, and that's the tricky part. But it shouldn't be enough of a difference to make a big difference. So there should be a slight advantage for the lighter thing. Should be easier to push. The light mass on the outside should be easier to start. But once it's rolling, it shouldn't matter. All right, something like that. But yeah, it's complicated.
It's a problem, though. Like all of these things, it's a problem. If we've got to have some kind of weight that's significant in regards to the weight of the disc. And if you've got a heavier weight with more mass, then the bigger it is. And the bigger it is, the more difficult it is to arrange in the 2 positions on the wheel. You can see on this little wooden disc that I would have trouble with this weight, putting it at 1 radius, half a radius, and at the full radius. So, alright, you want a bigger disc, and that becomes a problem. You've either got to cut it out of wood, which is difficult.
Take 2 frisbees, so make a double wheel. Then you can evade the problem of it falling over or twisting or turning. So you can always use a double wheel and just do the same thing to both wheels and blah blah blah.
You want something about 1 foot wide, really, to stick the heavier weights on. So you get a problem getting the big enough disc. And if it's not thick enough, if it's too thin, then it will tend to deviate and it won't roll straight and wobble and fall over. So that's another problem. So just to let you know, I am attempting to find a way of doing this experiment, but just to point out, nothing's easy, is it?
Right. Well, see, there's so many ways you could do it, and that's sort of the argument, is that, yeah, you should think about it before you do it. We all have run out of patience with doing that, and but there is, like, I could theoretically say, okay, if you did with a 2-wheel thing, so you have the same cart, then you could really just put the lever right in between. You could have a 3rd wheel, okay? It doesn't even have to hit the ground, and really you could just put on that 3rd wheel. It's this way. I'll tell you, damn this glare thing. Well, it's a little better. Alright, so, and then the 3rd wheel could just be where you just do your lever thing, where you put the one case that way, and the other case would be twice the mass, evenly spaced in the center, twice the distance from the circumference, from this distance. So make that wheel in the middle, so do those 2 versions, and have that on the same wheel in the middle. Should be the same thing, should equalize all of those variables, and then you just time it. But if you want to do the side-by-side comparison, then obviously you need 2 of these cart things, and it gets more complicated, blah 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 blah. But lots of different ways to do it, and I'm sort of inclined to say it would be good to do it in the horizontal fashion, because then gravity is only friction, and so the 1 wheel with the 4 mass will weigh more, create a little bit more friction on the bearing, but that shouldn't be that significant. And at least you're not going up and down in gravity, so you don't have to worry about how much. It should be the same energy to rotate it, compensating for the fact that you have a little extra mass from in the one case there's twice the mass, which makes the whole wheel itself weigh a little bit more. But yeah, those are real considerations. But frankly, the the difference shouldn't be enough to account for the difference in the statement, which is the ones on the outside have twice the energy or take twice the energy to move. I don't think it's going to be anywhere close to taking twice the energy to rotate the disc with the weights on the outside, the lighter weights further out. So it should at least prove that it's nowhere close to twice the fuel to go, 4 times the fuel to go twice as fast. That's not going to come out to be true. All right. So, back to the video.
The other thing, to address what you were saying about physicist Michael and his claim with the lever experiment being wrong.
All right, so I guess we have to go over this because, I mean, I thought, I've made so many videos on it pointing out all these things, and it's like, okay, you don't have to believe me, but I did play the clips. The truth is, it's just an established fact that he has predictions, and they're predictions for certain experiments. And so the experiment we talked about, and eventually he did do, is pretty simple, and I'm surprised that you seem somewhat confused about that simple experiment. So you just have the lever, and the idea I pointed out, the first thing you want to do is find out how much energy the lever itself absorbs. So the first thing I do is crash a thing into it and then see how much energy you have coming out. How fast is it going after it moved the lever? So that would be interesting just to know. And the second experiment really is just to do the mass here, the same distance, and just see if you can get this energy to lead to this, which is simple enough. Now his prediction was this bounces back with 1/2 the velocity, and this leaves with 1/2 the velocity. Now you should be able to concede that that's nowhere close to what happened. Okay, what happened was there was almost no bounce here, and that happened in his experiment also. This was if if this is going a 1, okay, the bounce was 0.02. Okay, 0.02. I mean, it was a tiny amount of bounce. 1/100th of the energy that went this way bounced back this way. Tiny amount of bounce. Just like your experiment, very little bounce, if any. And but clearly, half the energy didn't come back as a bounce. So clearly his prediction was wrong. And this is obviously much more than half and close to 90%. And I think we've already well established that this is the only part that matters about how much energy the lever itself uses in moving. It's mass, and it's going to move. And it doesn't matter where it stops moving, it just matters that it had to move. It took energy to move it, and the energy to stop it is going to be, likely to be friction or some other mechanism, and it's not going to be because the energy went into the other object. So the 90% is just a consequence of the practical matter of having to move the mass of the lever. I mean, it's real mass, has to be moved, and that energy isn't going to get into here because it's in the lever. So that's the limitation of the experiment, is that you can't get better. Maybe you can do 95%, maybe you can do a little better, but the point is the lever is going to take some. And you can't really avoid that. All right, and so then the second experiment, I'm surprised that you're debating whether you'll do it or not when it's the critical experiments. The whole point of doing the lever experiment is to demonstrate this circumstance where you're going to put the 2 mass here. Here's the fulcrum. And you're going to put the 1 mass out here, twice the distance. Now, the simple argument I've made is that when you're going to do that experiment, you have to account for the fact that you're losing energy to the lever. So the position of this can't be that position because it's not going to be enough energy to move it at this speed. This speed requires 2x the velocity. It can't go 2x the velocity. because some of the energy is getting lost to the lever. So the fact is that you're going to have to move this in just a bit to make it a little lighter so it can go at a faster speed. It'll be less bounce. So the point is if it's out here, anything I put further out here, I make heavier. So if I put the weight too far out, you can figure you're going to get a bounce because it's way too heavy and it can't move it. So more bounce for more weight. Less bounce, okay, the further this way I put the weight, the more likely that this thing continues to go through. It doesn't stop, it just keeps going through the lever. So the extra energy either is going to come back as a reflection or as this. And there's certain one specific location, so there's only one location you can put this where you get neither a reflection or neither going through, where it uses all the energy, gets into the lever. And that's the spot you want to find. And it's technically not going to be a calculated spot because you can't be sure of exactly how much energy is going to be absorbed. So you have to just find it. So find the spot where it reflects, where you get the most energy this way and the least energy this way or that way. But anyway, that's the basic experiment. So that's the one we need to have done. That's the one I want to see, and I would assume everybody else would like to see, without any interfering springs or other devices. And my argument about springs, and I just want to make it again, isn't that springs would necessarily get in the way. If you had this exactly where it's supposed to be, the spring probably wasn't going to make much difference, especially a stiff spring. But, we're not at that point yet. And as I point out, the softer the spring just means it delays everything. So, its compression expansion is slowed down, and obviously any delay isn't going to work because the object's already leaving, and it taking its time means it's going to just lose more energy to the lever. It's going to, well, whatever. I think I made that point well enough. So those are the experiments. So in the first one, he failed to get the correct prediction. Now, in this 2-to-1 one, all right, so let's erase all this extra proliferatory stuff. Get rid of that. Okay, in this experiment where you drop the two mass at one distance and you have the one mass out here at the right location, his prediction was, right, my prediction is it's twice the velocity. Okay. His prediction was 2/3 this velocity. Now, obviously, the outcome of the experiment was this one did go more like 4/3. All right. I mean, maybe it was 1.4. I don't know. I didn't bother doing the calculation. Okay. 1.4 is close to 4/3. Okay, pretty close. But that's what the outcome was. And you had a huge bounce. So you got a big chunk of bounce. So 1/3 of the energy stayed here as a bounce. And 2/3 of the energy, you could say, went the other way. But it went with, obviously, more than 2/3 the velocity because the mass is half as much. So it obviously did go faster than 2/3. So his prediction was wrong here also, just pointing out. And obviously my explanation is merely that the energy you had lost in this bounce with twice the mass, if you doubled that velocity and added it to the object that went 4/3, you'd end up getting a lot closer to that 85 or 90% of the velocity. So without the reflection, you get twice the velocity on this side, add that to the 4/3, and now you're getting a lot closer to having 5.5/3. All right. So we will continue.
This incoming weight pretty much stops, which of course is what you'd want to transfer most of the energy.
Obviously, so it's working as I suggested it should. So that's the point. Not as he suggested it should. He's clearly saying that this momentum in the opposite direction is completely not correct, in the sense you can't convert the momentum from this direction to that direction and say that adds up. 100 in, 100 out. That doesn't add up. It has to be 100 continuous in the same direction. You can't change direction by their rules. If you change the direction of the energy by their rules, that's free or negative energy.
I think that Michael come up with a claim that the velocity of the outgoing mass would be 2/3.
See, you're messing the two experiments up. The 2/3 thing shows up when he starts talking about twice the distance at half the mass. So the same mass should, at the same distance, was 1/2 and 1/2. That was his prediction. Half the energy is a reflection, half the energy goes to the other side. And they both go in the same direction. And somehow that's okay. So the energy came in one way and it leaves in another way, and that's okay because twice the energy went into the fulcrum, whatever that means.
Of the velocity of the incoming mass. And a long way short of our predicted 1.4.
So the 1.4 thing doesn't have anything to do with this experiment either. You don't predict 1.4. Okay, you predict 1.4 with the half mass. The half mass at twice the distance is where your prediction is 1.4 and my prediction is 2. So this one, your prediction is, I don't know. See, it doesn't make any sense, right? What can your prediction possibly be? I mean, you're saying that twice is going into the fulcrum this way. So there's energy going with twice the magnitude this way. So obviously you have to have energy going back because you have to get rid of that 2 and turn it back into a 1. Their theory wants to say 1 went in and 1 has to come out. That's what has to happen. And they're saying it came out in the direction of the fulcrum. So you move the Earth with 1. So the energy went from the solid objects you moved. This went that way. Okay, well, 1 went this way, right? If you add up the 2 halves that he predicted, or if you just add up all the energy going back on one side, that's still a 1. And then you have a 2 going this way, and so you subtract this 1 from the 2, and you get 1 going that way, so therefore you've conserved the momentum because you conserved the direction. Now, obviously, I'm arguing direction has nothing to do with it. The lever's whole purpose is to change the direction of the energy. That's its function. So why would I be surprised? I pull down on a lever, it pulls up on something. I mean, it's just obviously changing the direction of the motion. It's changing the direction of the pushing force. I push down, it pushes up.
Times the velocity of the incoming mass. So where's that lost velocity gone? Well, when Michael was starting to talk about this experiment.
So again, you're really not paying much attention to what Michael says. So again, you're telling me what Michael talked about, and again, you're getting it so wrong. So, I'm just saying, for this experiment, he predicted half and half. For the 2-to-1 experiment, he predicted 2/3 the velocity in the lighter object. So he's saying the lighter object only goes 2/3 the velocity of the heavy object, not 1.4. So he's saying 0.7, not 1.4.
I must admit, I was a bit surprised myself when he was making a big thing about the incoming mass sticking to the lever. I thought, I don't. Who cares about it sticking? I thought, I don't care whether it sticks or not. But of course, this, as you say, Gary, this is physics takes a bit of thinking about. You're very good at that. And
that's a monstrous concession. Thank you. I'll say thank you. I do work at it. I mean, I spend a lot of time figuring out, well, what are all these little stupid variables?
Because it's not always straightforward. The business about sticking to the lever, I think, is very important now. And I think that is where this prediction of only 2/3 the speed is coming from. Because
If it sticks, it's definitely going to have to force the energy into the lever. But my argument is you don't have to force it. It should do it naturally. But ideally, yes, it'd be even better. You want to put a piece of Velcro on here and make the weight stick to the lever. It can't do anything but help force more energy into the other side. It can't hurt, as far as I can see.
when I do this, it's not sticking to the lever, but we're getting a good energy transfer. Now, if it came...
It's a little hard with pendulums to tell what's a reflection and what is a going forward and then just swinging back. So the two require, a video that you can play at a slow enough speed to see the difference.
Came in and did stick to the lever, we've now got, we had the velocity of the incoming mass, and we've got the velocity of the outgoing mass. But if the incoming mass is stuck to the lever, we've got to account for the kinetic energy still in this.
Well, you might as well just say momentum, right? Kinetic energy is made out of momentum. So you could just say momentum and you're still covered for kinetic energy. But whatever. Yes. So that was also already in the video. Look, when he did his formula, this equals this equals this, and then did his whatever, his little fancy third thing. That third thing is the lever, okay? The angular momentum thing he was measuring was the momentum left in the lever. So that was already known from the beginning that we're going to have to account for moving the lever. It has a mass, it's going to move, and it's not going to stop moving by magic, so its energy is lost. It's going to stop moving because of friction or some other thing, so that energy is lost energy. Lost momentum.
In this system, the kinetic energy of the rotation of this lever with the mass.
Whether the mass is attached to it or not, the point is the mass is going to deliver the energy to the lever. The lever's delivering it back to the mass. The whole idea is to make that process so quick that there aren't any opportunities for losses. So you want to try to make it Newton's cradle kind of quick. So it's very efficient. Because if anything that slows down that transition, that translation of the energy, you could argue that anything that slows it down is going to disrupt the capacity to exchange the energy.
And I suppose if we're only getting 2/3, a predicted 2/3 out of it.
All right, so you still got that part wrong. His prediction for the equal masses at equal distance is 1/2, not 2/3. So he's not getting anywhere close to 1/2, so we already know that prediction failed. Completely failed.
Yes. The other energy is tied up in this lever with the incoming mass still moving.
So as you just did the experiment, it came out like 90. Okay, you got you got results that are pretty close to 90% of the energy in the other object. It looks like about 90% of the velocity, 90% of the distance. Obviously, you have to account for the pendulum. The fact is, it's the distance is easy for the first part of the travel, and it only gets difficult as it goes up that last little bit. So that last little inch is really important. There's a lot of energy tied up in that last inch because it's mostly going up instead of going sideways. So anyway, regardless, so if you just do the linear measurement, I'm just saying your results are pretty close to looking like 90. He did the experiment, he got 90. Okay, it came out exactly 90% of the momentum went into the other object. Now, he didn't acknowledge that was completely different than his 50% prediction. So you shouldn't be confused in the sense that the first experiment, this experiment did prove me right and did prove his model wrong. It's just a fact.
Still moving. If the incoming mass is going to stick at the collision and move, then the incoming mass is still moving. So we've got to account for that energy if it's still moving. When I do it here, it completely, well, it pretty much...
See, it does look like it does stop, okay? But it stops after it's gone past the center point. So it pushes a little further, okay, than stopping at exactly the launching point. But yes, it doesn't technically reflect. It just swings past and now it just swings back. So it has a little arc because it's going to keep its momentum, pushes it forward past the 0 point. It pushes the lever to push the other object. So in a sense, it does what it has to do. It has to keep going forward if it's going to push the lever to move the other object. It has to go past the 0 point. It has to go past the point where the pendulum would stay. So this is where the pendulum is 0. It's even in gravity. This is its bottom. The point is it has to swing past the bottom to push on the lever. So it obviously has to go further. All right, and the point is it doesn't appear that it's reflecting as it goes back. It's just swinging back.
That stops. There's not much energy left in this incoming mass.
There's technically no energy left in it because it swung past 0, so that was all positive energy. So anything left isn't really a loss. That's hard to say. It obviously had to move up against gravity, so it had to lose a little bit of energy. So yes, you have to account for the fact that you're going to lose a little bit from the pendulum having to go up against gravity, but because it's going in this bottom part, there's very little up and down, so it's mostly sideways motion. And that sideways motion doesn't equal much in here close. It's out here. So when the pendulum's swinging up, that's when you're doing a little tiny bit of distance this way, but you're doing a lot of work against gravity, up and down. That's when the distance really matters. Movement in the flat part is a little tiny bit of energy. Movement out here is a lot of energy.
And there's no energy in the lever. So that's, I think, where...
So obviously there was energy in the lever. It didn't just disappear, so it just got eaten up by the friction. But there obviously wasn't much because your lever didn't spin very far, or else your bearing is kind of sucky. Okay. Now, I could point out to you, I did whole arguments about how you don't really need to make a strict bearing. You just need to make a fulcrum. You just want a peak for it to rock on, because you don't need to spin all the way around. You just need to do this. So all you need is some pivot point. So you can make a very thin little wire, a very thin little point. And the smaller your fulcrum, the better your results are going to be. The less energy you'll waste.
Physics is doing this prediction. You've got to account for the whole system. It's not just the incoming mass and then stopping dead.
Yeah, we all did that already. So I'm just saying that in the conversation was clearly we both accounted for the fact that the lever is going to absorb some of the energy of the experiment, so we're not going to get all the energy out. But what wasn't really emphasized, as I tried to point out, is that you have to compensate for the energy the lever is consuming in recognizing the weight now can't be pushed at the same velocity because there's not enough energy to push it at that velocity, so you have to move it in a little bit so you can get its peak velocity, because it's going to weigh too much, because you don't have enough energy to push the same amount of weight. If you have an amount of energy going in that pushes 10 pounds and you lose some of the force to the lever, then you can't push 10 pounds anymore, if you get me. So now you have to compensate and make it 9 pounds because you lost the 10 pounds of force. You don't have 10 pounds of force anymore. You only have 9 pounds of force that's actually getting through the lever. So you have to make your weight weigh 9 pounds.
If the incoming mass sticks to the transfer medium, the lever in this case, then there's still energy in the system that has to be accounted for. So you would not expect the 1.4 on the outgoing.
So the 1.4 again is the 2 to 1 experiment. So you're just confusing the two experiments. His prediction was 1/2, and clearly it's nowhere close to 1/2, so it's a moot point in my opinion. And clearly you didn't get half the energy reflecting, so it should be a moot point for you also, and just say, whatever his calculation, it was wrong, and that's just a fact.
Mass. Sorry, there's a rocket trying to take off above my head. That's a washing machine. So, yeah, this sticking to the lever business is quite important, I think.
I thought you were in a garage, so yeah, your basement is as big a disaster as mine. Anyway.
And I suspect that's where that prediction is coming from. I don't remember in his video whether the cart's stuck to the lever or stopped or...
Yeah, well, they had springs or clay, so obviously we'll just throw out the clay experiments because they were just a waste of time, and recognize that they were all had one spring on the cart going in, okay, and they were all done that way, and but frankly it doesn't really matter. I mean, I'm still saying the springs don't matter if you have everything in precisely the right location. The springs shouldn't get in the way, but they will get in the way if you're trying to hit something that's, you have to, if you have the weight too far out, so it weighs too much to push, you can understand that now the reflection is going to be in play, and the spring just guarantees the reflection. So any mistake in balancing the weights, the spring will ensure that that mistake is very visible because it's going to allow the energy to reflect.
Well, what they did actually, I'd have to review that. But the point is that if the incoming mass doesn't stop and it still has energy going forward, that has to be accounted for. So you would not expect the 1.4 velocity on the outgoing mass.
Well, again, it has to go past zero to move the lever. I mean, to some extent. I mean, ideally, it'd be perfect, yes, if you could make this out of a perfect substance where the vibration goes clearly right into it, just like a Newton's cradle, and then the lever only has to move a millimeter. That would be ideal, but you're not going to find a substance that can do that. So it's always going to be a little bit imperfect. But the point is it's not going to be imperfect enough not to see the obvious difference between my prediction of twice the velocity for the lighter object and his prediction of 2/3 the velocity. Those differences are going to be obvious.
And the other thing is, it would be nice to do more experiments with this setup. But the trouble...
That's the whole point, yes. I don't know why you didn't think that's what you're sort of obligated to do. That's the whole point of doing this setup, is to challenge it and to test it in different forms, in different ways. So, yeah, you always, if you're going to bother to set up an experiment, you should always set it up knowing that you're going to have to change how it's configured.
Liz, I've got numerous holes now.
See, I don't know. Why not just put staples? Why put holes in your joist? So, yeah, I wouldn't have put holes in your joist.
Put into a joist with the washing machine above in the kitchen, and it's weakening the joist.
Yeah, you should just put screws in. So maybe you have to use your aluminum to secure your joists. But, about 10 inches above me, so the floor is pretty secure here.
And to alter bring the weights in, I'd have to drill more holes and things like that. So it's put me off a little bit. No other reason.
I mean, even if you chose not to do that, okay, you left these distances the same, you could cheat on the lever. So you could just move the lever over, okay? You have to move the fulcrum, to a new location on the metal. So you'd have to put a new hole in the metal. Because you could have an imbalanced lever, but it's not going to make that much difference. In the horizontal mode, it doesn't matter. You're still moving the same amount of lever, no matter how much is on one side and how much is on the other side. It ain't going to matter, because it's not about going up in gravity. So horizontally, an imbalanced lever is legal, okay, because it's not going to steal energy in any imbalanced way. Moving the lever this way or moving the lever this way is the same work. So it's not going to make any difference when it's horizontal. So in that sense, if you wanted to cheat by just moving the fulcrum, that is, put a new hole in the metal, leave everything the way it is, put a new hole with a new fulcrum that's where there's 1 unit of distance on one side and 2 units of distance on the other side. So just move your screw or whatever to this location. Then you just have to put the half mass out here, and you could. It's cheating, but it's a cheat that's probably allowable because, like I said, technically, it doesn't make any difference. You're moving the same amount of metal. It doesn't matter which way you're moving it. It's going to steal the same amount of energy no matter where you put the fulcrum. Okay, I'm pretty sure of that theoretically.
Although I might be able to get around it by doing something, because you want these pendulums in a V formation, so you've not just got one string suspending it, you've got two. If you just have the one, they twist and wobble and everything, but the V formation of the 2 strings gives it.
You have to sort of try to get those distances the right way too. They should have the same V, I guess, the same length of cord or whatever, with the same angles and all that kind of stuff, because some of that probably matters a little bit, but probably doesn't matter much.
Stability. It would be quite interesting if I had a 1 mass coming in at 1 radius,
2.5 mass.
And a half mass at 2 radius.
Right. So you just got to find something that weighs half as much as this thing, that has the same profile and will hit with the same, the same solid object. If you try to attach objects to it, well, then you're going to lose the ability to transfer the energy efficiently. So it really has to be a solid object, ideally.
2 distance going out, and see where that reached. Now, if we're saying that the half mass 2 radius 2 distance only gets 1.4 of the velocity.
Yeah, well, that would take it, if you pulled it back halfway here, then 1.4 would be here somewhere. Yes, all of that mush.
Could we predict that it might only go, if that's halfway, would it go 1.4?
It'd only go 1.4 if you only move this half the distance. So again, but then we're doing the gravity thing, so you have to recognize that half the distance isn't really half the distance in the gravity. You didn't raise it up halfway because it's a pendulum on an arc. So you have to get these distances right. The distances aren't going to be the same. You have to get half the height. Not, and we know that it's 4 times the height, so we know that's different too. So again, you can't do this. You can't just do a straight ruler measurement. It's not going to give you the right answer.
The distance between the start and the lever collision, that might be interesting to do, to at least see the difference that this mass would then fall short of getting to the start place in comparison to the...
Obviously, there's enough of a difference between 1.4 and 2. So obviously, my prediction is it going twice as fast. But twice as fast isn't going to be twice as far, because of that fact that you're raising it up higher. With every little millimeter you go further distance on the outside. So you have to do, it's a calculable equation, but I'm just saying I can't do it off the top of my head what the ratio is going to be. But 1.4 is going to look like 1.5. You know, that's going to be where it gets a little sloppy.
Equal mass and equal distance. Should it go not as far? Because it hasn't reached the same velocity. That's something I might try, if anybody thinks it's of interest.
Seems kind of bizarre that you don't think the most important experiment, the one that's going to decide this one way or the other, is, oh, maybe it's worth doing. See, I'd like this one to make the conclusion, you know, the same mass, but obviously the kinetic energy is the same. Same kinetic energy in, same kinetic energy out, because it's the same mass. So there's, you know, this isn't very challenging. Even though physicist Michael's prediction was wrong, you could still say kinetic energy was conserved because I have the same amount of kinetic energy in the universe. I have something, a weight, moving a certain velocity and mass, and it's the same amount of kinetic energy. But yes, his theory is wrong. Okay, his model is wrong. But yes, you could understand it. I could understand it as you know, that the same kinetic. If kinetic energy was real, I would understand that yes, I put 100 in this side, I got 100 out this side. Okay, I conserve the kinetic energy. And it's only when you change the masses that, and now do the conversion, because of the velocity being squared, that it becomes obvious one of these theories isn't going to conserve. One of them is going to fail to conserve. I'm saying momentum always has to be conserved, so it's really not an issue. You're going to have to find the momentum, but you can't kill it. All right. And you certainly can't make free momentum, and that's what conserving the kinetic energy will require you to do. But whatever. We'll wait and see.
Well, anyway, bye for now.
Okay.
Hello, guy.
I guess we'll reload it and see if there's any comments. Alright. No, surprisingly, 0 comments. Alright, so, yeah, enough of a video. Yeah, so, like, again, unless somebody else does the experiment right, I mean, eventually I'll have to do it, I guess, but, yeah, I'm not there yet. And it should be done as carefully and as well as possible and all that mush. But it really should be a visible difference between 1.4 and 2. And there certainly should be a gigantic visual difference between 2/3 and 2. You know, 2/3 and 2 that's gigantic. Alright. So, till the next time and such and so forth and whatnot. Yeah, that's probably enough.